Okay, we are in chapter 3, section 7, and we're talking about electronegativity and molecular polarity. So we know that we're making bonds and we're making compounds with those bonds, but when we talk about those bonds, what a bond really is the sharing of electrons. And all atoms don't share equally, right? Some atoms want to attract those electrons more than others. And so we call that electronegativity. So the more you want to attract those electrons, the more electronegative you are. So the element on the periodic table that has the greatest electronegativity is fluorine. And so the closer you get to fluorine, the higher your electronegativity gets. And so if we look at the periodic table, but in this case, the only numbers that we're going to write on the periodic table are the actual electronegativity values for the elements. So if we look here at fluorine, fluorine has the highest electronegative value on the entire periodic table. It is 4.0. That's the highest you're going to get. This is the element that wants electrons the most. Will take electrons from anybody. So I call fluorine the floozy because fluorine will take electrons from anyone. And so as we get closer to fluorine, right, our electronegativity will increase. You see we go from lithium, that's 1, beryllium 1.5, boron 2, carbon 2.5. What's happening? We're getting higher and higher. So as we go across the periodic table, our electronegativity increases. And if you look going in this direction, so we're going basically from the bottom of the periodic table up, we go from 2.1, 2.5, 2.8, 3, and 4. So you can see you also have an increase going that way. So if you just remember that fluorine is the most electronegative, and you're trying to compare any two elements, you know the closer you are to fluorine, the more electronegative you are. So if we have two different atoms that are involved in a covalent bond, then they have different electronegativity values. They want the electron a little bit differently. One is going to want the electron more than the other. And so those electrons end up being shared unequally. So if you think about like hydrogen bonded to a chlorine, right? And you're going to end up with something that looks like this. That's going to be your Lewis structure, right? So that line that I drew there is a covalent bond, right? It's two electrons, one from hydrogen, one from chlorine, and they're sharing them. But are they sharing them equally? Well, if you look on the periodic table at chlorine, if I could erase some of this, right? We're looking at chlorine and we're looking at hydrogen. Right? They have different electronegativity values. Chlorine has a higher electronegativity value than hydrogen. So chlorine is gonna be greedy and is gonna take the electron and keep the electron closer to itself than to hydrogen. And so it's gonna be an unequal sharing. But when you have two identical atoms that share an electron, the electron is shared equally. So if you had, for example, two hydrogen atoms and they were in a bond, right? Each hydrogen has the same electronegativity value. So the electron is going to spend as much time with the first hydrogen as it does the second hydrogen. So anytime we have a bond where the electrons are not shared equally, as in HCl, right? This is a polar covalent bond. We call it polar, polar meaning unequal. So polar means unequal. But when you have electrons that are shared equally, then the bond is called nonpolar. So an example of nonpolar is some kind of equal sharing, as we saw in H2, right? Now they're both covalent bonds because they're being shared, but they're being shared differently. A polar covalent bond is unequal sharing, so you have two different atoms. And a non-polar covalent bond, you have equal sharing, so you have the same atoms. So let's look. When we draw this, what we tend to use to show that uneven or unequal sharing is the lowercase Greek delta. And the Greek delta means partial. So if we look at our example here of HCl, what we know is that chlorine is the one that's going to pull in that electron more because it has a higher electronegativity value, right? What do we say? Chlorine was a 3.0. Ooh, I'm zoomed in so far. 3.0, whereas hydrogen was a 2.1. So we look at our electronegativity values, and our arrow is going to point to our negative, and the little plus part of the arrow is going to be towards the positive end, right? So think about it. Wherever the electron is going to spend more time, it's going to be more negative. And now if that electron isn't sitting around by the hydrogen all the time, then the hydrogen becomes partially positive. And so that's how we denote it with that little sigma. So you could do it one of two ways. You can do a sigma. When you do sigma, you kind of, ooh, that was terrible, kind of like this. So this is a partial positive, and then this is a partial negative, right? Or you could denote it with an arrow where the arrow head is pointing towards the negative, and then the plus part, that part of the arrow is by the positive. Okay, but it's just showing that the electron is going to spend more time with chlorine than it is going to spend with hydrogen. And so it gives this an unequal sharing of electrons, right? So this one is polar covalent. Whereas if we look over here at H2, H2 is nonpolar because they're both hydrogen. They have the same electronegativity. It's 2.1 and 2.1. So the electrons are shared equally between the two atoms. Okay, so let's see, what did we say? We can denote it using the symbol, the lowercase Greek delta, or we can do the arrow. All right, so now, anytime you have to use those arrows or you have to use the delta symbols, what you are telling me is that the bond is polar, right? And so look at polarity in order to determine overall polarity of an entire molecule. So we're going to look just at bonds, and then we got to remember that those bonds occur inside of molecules, and we're going to have to talk about the molecule as a whole. So here's some examples, a few more examples of just bond polarity, right? In simple molecules that have two different elements, two different atoms, right? You could have something that is nonpolar. Nonpolar means that we're sharing them equally. Like you could have H2, you could have Cl2, right? You write H2, Cl2. Anything that has exactly the same two elements. You can have where we have an unequal sharing. We're sharing, but we're not sharing very well, right? And so, for example, we said maybe this was hydrogen and this is chlorine, right? Where this little blue area is the space around the hydrogen atom, and the red is the space around the chlorine atom. And what you can see is that there's a much bigger electron cloud around chlorine. So the electron's spending lots of time over there by the chlorine. And so we denote it with a little sigma, positive and negative, or you could draw one big arrow and just point it towards the negative and put the kind of a hatch on the end of the arrow to make a plus sign, and we put that on the positive side. So here we have polar. So the way that we do this to determine what kind of bond it is we look at that electronegativity difference. So if you look at your hydrogen, right, if we go back, the chart I keep going back to is here, right? Hydrogen is 2.1. So 2.1 minus 2.1 is 0. So if you look at that, here, hydrogen 2.1 minus 2.1 is 0. And that's what we're seeing here. We have an electronegativity difference of 0, so we are nonpolar covalent. Now, as we begin to increase the size of our electronegativity difference, we begin to get polar molecules, right? So hydrogen and chlorine, hydrogen we said was 2.1, chlorine was 3.0. So our electronegativity difference here is 0.9. So that would make us polar. So anywhere between 0.4 and 1.8, we have something that is polar. Now, if your electronegativity difference gets higher than 1.8, what happens is instead of sharing that electron, the electron actually gets transferred. And if you remember, when you're transferring electrons, when you're giving and taking, you're making ionic compounds. So maybe in this case, this is NaCl, right? That's ionic. So if we go and look on the periodic table, Na is 0.9, chlorine is 3.0. So if you subtract the two, right, you get 2.1, right? 2.1, and it's the absolute difference. There's no positive or negative. It's just the absolute difference. So 2.1 is greater than 1.8, so it's over here, so it is ionic. So this might be 2.1, right about there. So you have to remember, if you remember this 1.8 to 0.4, this is polar covalent, right? Anything greater than that is ionic. Anything less than that is nonpolar covalent. So that's the big keys to remember there. All right, so I think this is just text of the same thing, right? Elements with electronegativity difference of 1.8 or more will form an ionic bond, and that's that transfer, give and take, right? And so the electrons go to the more electronegative element. If you have something less than 1.8, you're going to share, right? And the greater the difference in electronegativity, the more polar the bond. And we'll look at a few examples. When we look at our different examples of ionic bonds versus covalent bonds, you can really look at the type of elements present. You don't actually have to do all those calculations. You know already that an ionic compound, right, ionic, right, is usually a metal and a non-metal, right? You can look at that. You don't have to go and calculate the electronegativity difference. Whereas a covalent, V-A-L-E-N-T, y'all know what I mean, covalent, is a non-metal and a non-metal, right? You don't actually have to go and calculate that. What gets trickier, though, is to distinguish between completely nonpolar, slightly nonpolar, and like really nonpolar, really polar bonds. And so if you remember fluorine the floozy, right, that is the most electronegative of all the elements. And electronegativities increase as you go across towards fluorine or you go up towards fluorine, then you'll be able to figure it out. Not a big deal. So the farther apart the two nonmetals are, then that's going to tell you that they're going to have a greater electronegativity difference and therefore a greater polarity, except carbon and hydrogen. Carbon and hydrogen bonds do have a difference, right? If you look on the electronegativity chart, carbon is 2.5 and oxygen is 2.1. Gives you an electronegativity of 0.4, difference of 0.4. That is not zero, but it's really close to zero. And so we basically say that carbon-hydrogen bonds are nonpolar because the difference is so small. So that's one thing to just kind of keep in the back of your mind. So because bonds can be polar, that means that molecules can be polar. And so we said in a polar bond, right, those electrons are unevenly distributed between the two atoms. Well, the same thing is true for a polar molecule as a whole. The molecule itself has an uneven distribution of electrons, whereas a nonpolar molecule, the opposite, has an even distribution, right? So even, equal, uneven, unequal, right? Those were the terms we kind of used before. If you have a really, really simple molecule, like when we did the HCl, right? If the bond is polar, the molecule is polar. So in this case, HCl is this bond. So the bond is polar. And because there are only two atoms, and there's only one bond there, that means that the molecule is polar. Now, if you take a molecule that has 3 or more atoms, and we have lots of bonds inside of them, what you do is you look at all the bonds and you look at the shape of the molecule. The shape of the molecule is going to help you to determine if it is electronegative or not. Let me show you what that means. Let's look at 2 different examples, carbon dioxide and water. They both have a central atom with 2 atoms around it, right? When we do the Lewis structure for carbon dioxide, what we see is that we have carbon in the middle, and then we have oxygens on either side. If you look at the bond between, let's say, just this oxygen and this carbon right here, what you can see is, if you go to your table, right, oxygen is 3.5, carbon is 2.5. So that's an electronegativity difference of 1. Well, what direction is the arrow going to point? It's going to point towards the negative, the more negative one. So oxygen is 3.5, it's more negative. And you put the little plus sign towards the less electronegative atom. So we have 1 atom that's partially positive, 1 atom that's partially negative. So you could either do it with those little sigmas, or you could do it with the arrow. And then I'm going to do the same thing for my other one. And I'm going to draw an arrow towards my electronegative element, okay? Because this one is also 3.5. And it is more electronegative than my carbon. So that's the direction I want to put my arrow in. If I do the same thing for water, hydrogen is 2.1. When we said oxygen was 3.5, 2.1, right? So now I'm going to point at my more electronegative atom. My more electronegative atom is oxygen, so I'm going to point this way. And I have to do the same thing, and I'm going to point this way. So when you look at these 2 molecules, you have to take into account the bond polarity. That's what we did. So both molecules have polar bonds, but we haven't taken into account the 3-dimensional shape of these molecules. So remember when we talked about Lewis structure, right? If you have 2 areas, so carbon dioxide has 2 areas of electrons and no lone pairs, that tells us that this is going to be a linear molecule, right? And so when we draw it just like this. It is linear. When we look at water, on the other hand, water has 2 areas of electron density that are bonds. So 2 areas that are bonded. And then it has 2 areas that are lone pairs or unbonded. Unbonded or non-bonded, however you want to say that. So you really have 4 areas there. So what ends up happening is that water becomes a bent shape because these electron pairs take up so much more room than a bonded pair. And so the water molecule is actually bent. So if you have something that has polar bonds but is symmetric, what you end up getting is a non-polar molecule, right? A linear shape is symmetric. If you have the same atom on the outside, right, and you have these same arrows, what actually ends up happening is these arrows cancel each other out. And so you actually end up having a non-polar molecule. But water, we don't cancel each other out. They're pointing in different directions. So if I wanted to put 1 overall, let's say I wanted 1 overall arrow, this would be the overall polarity of my molecule. So this one is polar. So water is actually polar. It has polar bonds, but it is asymmetric. ETR, asymmetric. And that means it will be a polar molecule. Okay? So look at the bonds and then look at the shape. So if the shape is asymmetric, then it's going to be a polar molecule. If the shape is symmetric, then it's going to be nonpolar. All right. Okay, so I think this is just verbally saying everything that we already did. So we said CO2, right? We do have polar bonds, right? But those electrons are being pulled in opposite directions. And so the dipoles cancel each other out. Polarity, dipole, same thing, right? So they cancel each other out and we end up with a nonpolar molecule. The electrons are spread out equally over the entire molecule. So we get nonpolar molecule. Okay. But where water had that bent shape, the bent shape is asymmetric, right? The bond poles don't cancel each other out. So we have this overall dipole moment inside of this molecule. And this is really, really important for how water molecules interact and all the properties of water that we know. I mean, it makes water super unique. And so when you look at a molecule, you have to look at the individual electronegativities to determine your bond polarities. And then you have to look at the overall shape. And so we're going to do that. We're going to go and look at a couple of in-class problems here, right? So for each of the following molecules, we're going to draw the correct Lewis structure. We're going to label our polar covalent bond with a dipole moment arrow. And then we're going to determine if the molecule is polar or nonpolar and draw the dipole moment arrow for the molecule. Okay, it's not that bad though, really, it's not. So HCl, this is kind of one we just talked about, right? We have our normal, and you could do the needed, available, shared. I'm just going to assume that you know how to do that by now. So what we know is that there is an electronegativity difference, and you have to go back to that table in your lecture notes, right? So I know that my hydrogen is 2.1. I know that my, Cl, not carbon, Cl is 3.0, right? So I'm gonna point at my more electronegative atom, right? So here's my bond polarity. Well, in this case, my bond polarity and my molecular polarity is the same because this is a simple molecule with only 2 atoms. So I can say that this is a polar molecule, right? All right, let's try another one. Let's try B. COS. Carbon is going to be my central atom. And I'm just kind of told that. So I'm going to put carbon here. You can do needed, available, shared. I know how it's going to go, so I'm just going to add them in myself, right? Okay, now I need to go get my electronegativities. My carbon is 2.5, my oxygen is 3.5, and my sulfur is 2.5, right? And even if you didn't have these numbers, what you can do, which you actually have to do, is to remember, right, fluorine the floozy. And so if I look at fluorine, then I have oxygen, nitrogen, carbon, right? And then I'm coming down, I have chlorine, I have sulfur, right? Okay, so here are all my elements. When I want to know what's more electronegative, if I'm talking about sulfur and carbon, what I'm going to look for, right? Sulfur and carbon. Oh, actually, that one I would actually give you because they actually have the same electronegativity. So I'd actually give you that one. But so what we can say is this here, see if I can draw this. This here is a non-polar bond, right? So I'm not going to draw an arrow for that. But now I need to look at my carbon and oxygen. Carbon and oxygen are in the same row. And I know going this way increases my electronegativity because fluorine's my most electronegative atom. So even without a table with all these electronegativity values, you can tell me that oxygen is more electronegative than carbon because it's closer to fluorine, okay? So then I would draw my arrow, and I want my arrow to point at my more electronegative element. I'm gonna put a plus sign by the carbon. So I have one bond that's nonpolar, and I have one bond that's polar. So if I'm going to draw my overall bond, overall molecule polarity, it's actually the same for this one as the bond because there's only one bond that has polarity. But that makes this a polar molecule. And these are both polar covalent. Polar covalent, right? Because we have a metal and a non-metal. Because we have two non-metals. Okay, let's do C. We got H2S. We know hydrogen cannot be a central atom, so sulfur must be our central atom. And when you draw this, you would end up figuring out, looks like this. But remember, in 3 dimensions, it's not actually like that. Actually, you have sulfur, and remember that our lone pairs end up taking up so much space, right? That it pushes those hydrogens down. So you have to think in 3-dimensional space. You have to look and say, oh, I have 2 lone pairs on my sulfur. So that tells me that I'm gonna have a bent geometry, and we're gonna have we're gonna have an asymmetric molecule. And so we might have a polar molecule here. So let's see what happens, right? So if we look, hydrogen, right? Hydrogen and sulfur, hydrogen's way over here on the periodic table, right? So we know it's basically not gonna have the same electronegativity, but if you look it up in a table, it's 2.1, and our sulfur over here is 2.5, right? So your book calls this one polar, but it doesn't call the carbon hydrogen polar, which I don't necessarily agree with, but it's okay. We're just going to say that the only bond that's non-polar that actually has an electronegativity difference is carbon and hydrogen, even though hydrogen and sulfur have that same difference. It's just the way it is. All right, so my sulfur is my more electronegative, so I'm going to point at that one and put the plus sign by my other atom, point at my more electronegative. So if I add up those 2 dipoles, what I'm going to end up with is a dipole moment that looks like this for the molecule. So the green one is for the molecule, the 2 blue ones are for the bond. So if we're going to look at this, right, our SH bonds make it polar, and so the molecule is asymmetric, it's bent, so this is a polar covalent molecule, right? Okay, let's see. D. Okay, so D is CH2Br2, and we're told that carbon is the central atom. So let's go ahead and put carbon in as my central atom. 2 of the atoms are going to be hydrogen, and 2 of them are going to be bromine. And it really doesn't matter so much where you put them. If you remember when you have 4 things around the central atom, right, it was kind of, we did this little dashed thing, and I'm really not a good artist. And then we had one kind of coming out at us, right? So if you kind of remember to think in 3 dimensions, that's a good thing. So we end up with something that looks like this. And it doesn't really matter where you put the hydrogens and the bromine. Okay. So if we look at this, we have to think about our electronegativity differences, right? So our hydrogen is 2.1, our carbon is 2.5, but we said really that's no difference. So we're going to say that that's a non-polar bond. But our bromine, right, is 2.8. So we do have an electronegativity difference, and I think my picture's covering that. 2.8, we do have an electronegativity difference between the carbon and the bromine. So we need to show that. So we're going to say the bromine, right, is more electronegative than carbon, which is 2.5. And so we're going to actually point towards the bromine, and we're going to point towards the bromine. And so because we have these nonpolar molecules, nonpolar bonds, if we draw one arrow that combines all of our electronegativity differences, we would basically draw something like this. And so we do have a polar covalent molecule, right? Even though this is a symmetric 3D shape, it is actually asymmetric because we have some atoms are one element and other atoms are other elements. So if this were CH4, right, where we had like one going out the back, and these were all hydrogens, then this would be nonpolar because it's all the same. And even if it were bromines, right, something with an actual electronegativity difference, right, if it was CBr4, what we would see is still it's nonpolar because all the atoms surrounding that central atom are exactly the same. So that would be nonpolar because even though we have bond polarities, and I would draw this for all of my bond polarities, right? Overall, I have all the bond polarities cancel each other out, and overall I would have a nonpolar molecule. But here I have 2 bromines and 2 hydrogens. And so because I have different atoms surrounding that central atom, it makes this molecule polar because it actually ends up being asymmetric. Okay, and that is, we only have one other problem in there to do, and that's it. Okay, y'all have a great rest of your day.